Yes, big data on data you don't have. So a couple of years ago, a guy here gave a presentation on big data, and he claimed that it makes you grumpy, right? But in reality, when you don't have the data, it makes you even grumpier, right? And there's a lot of times when you really don't have the data, because a lot of questions are open to interpretation. How many apples do I have at the grocery store today? You can probably answer that question. How many apples might you have tomorrow? Well, I don't know. You could probably have to model that, guess it, look at your delivery chains. And very quickly what you realize is that big data on data you don't have, one of the things that makes it difficult is that it's infinite dimensional, right? And so the question is, how do you deal with infinite dimensional data? And the way you deal with infinite dimensional data, what we're going to do today is we're going to generalize traditional mapreduce paradigm. So we're going to take what you all know and love as mapreduce, and we're going to change it into something more general and that actually works with infinite dimensionality. So first off, disclaimer. There's two reasons I always think not to give a speech about something that you think you've done that's new. Like, reason number one is you have to hear your own voice potentially on a recording later, and that's like the worst. Reason number two is the fact that there might be somebody in the audience who's already done it. So if you've already done this and this isn't new, then just humiliate me after, not during the speech, and that'll be great. Okay, so let's break data into 4 buckets. So first bucket is data I have. That's your traditional big data, right? Data I can acquire, right? That's data that's you can go out and get. Data you can model, or data someone else can acquire or model. So something that somebody has to physically share with you. And really what you quickly realize is data you can acquire is, and data you can model is infinite dimensional. So data I have is like, what's the temperature in this conference room? Data I can acquire is, what's the temperature outside? I can go over there and acquire that. Data I can model is, well, what's the temperature in Malaga? Well, I know it's like 1 degree more, so I can just add 1 degree to the outside temperature, and that's, roughly. And then data somebody else can acquire or model, what's the temperature on planet Xandu? I don't even know if there is a planet Xandu, right? But, someone may have that data that I can go get, and I have to ask. I have no way to acquire it or model it myself. All right. So very quickly what you realize is data you can acquire and data you can model and data someone else can acquire is infinite dimensional, and data I have is traditionally finite dimensional. So you run into this problem of how do you start talking about infinite dimensionality of data, and all of your constructs about bringing the calc to the data sort of breaks down because that's quite simply you can't bring the calculation to infinite dimensional data. So the way I think about it, though, is that there's effectively 4 things: pre-calculated data, services, formulas you have, and things people can share with me, be it other data, other services, or other formulas. Right? Now, we all kind of know this paradigm, right? Pre-calculated data is in there. Maybe use a spreadsheet to input your own formulas. Services are like plugins into your spreadsheets. They go out and get some data. And so, when you think about what Excel does, it tries to grapple with some of these concepts. It's really bad at sharing, though. So what we did with the product that I'm going to talk a little bit about today is we tried to actually create a construct about how to work with all these elements simultaneously. Now, these are the guys who I worked with. I love giving credit where credit's due. The reason for the striped shirts, those are the managers. It's the only way we know who the management team is. So Dan and Dave manage the team and the server. We make this out of London, and Ian is our architect. Their names will come in handy later. So traditional big data you have paradigm. So this is what you normally see, right? I know I've simplified this a lot, apologies. You load a bunch of data into a big data repository, and then you put like something on top of it where you slice, dice it, maybe you run some analytics on top of it, you do other sorts of elements. Now, if you're in infinite dimensional data and you want to deal with services, what you want intuitionally is you want the ability to communicate to basically some sort of platformish server, and you want to go out and call remote services or remote data repositories. Right? And by calling these remote data repositories, you really create on-demand data. Services are nothing more than, again, it's data you can acquire. You go, you acquire it, you get it back. And so on the left, you have a hard time answering bespoke questions. So one of the things that I was involved with in the past was the peripheral, what we call the peripheral European crisis. So in my previous life, I was head of risk at Barclays Bank for the Prime Services division. And so, people would come in and they'd say, well, what happens to the markets if X happens? Well, you probably didn't put what X is into your big data repository. You had to go out, you had to calculate that and bring that back and then use that as a discussion topic piece. So on the right-hand side, you also want to put an expression layer over there because those are your formulas. Right? That's the data that you can effectively model. Right? So you have dynamic new data, data you can acquire, and virtual fields, data you can model. So intuitionally, you want something kind of like on the right. So what does that look like then? Well, by the way, that was my, do you like the animation? It's very subtle, but good. OK, so the way you start to think about this and you start to formalize this is by being able to answer complex questions. And I think industries have spent a huge amount of money being able to create systems that answer very specific questions, right? So, what happens to sea level if the temperature goes up? What properties on the beach and over X meters above sea level in Marbella? And then what's the biggest real estate bargains in a portfolio? You can probably go out and find those 3 systems somewhere in the world, right? And it's easy to get answers from each of them. But what's hard is when you start to form that into a complex question. And by complex, I don't necessarily mean difficult. I just mean it's got multiple nouns. I was horrible at grammar. Nouns and verbs and predicates and things like that. So what should I buy if I believe temperature is going to raise by 1.5 degrees and I only want property that's at least 1 meter above sea level but still on the beach? All right. You want to be able to write this. And apologies for not putting let's in front of everything, so it's not going to compile now, is it? But you want to write something like this. And then you want to send a little micro program to something like this platform thing here. And then it starts farming. As it executes the program, it starts farming those things out to different services to be able to answer that program. And that intuition is not only good intuition, it's actually correct. You really, to be able to answer complex questions, what you need is a compiler. Right? And that compiler needs to take in code, and that code needs to be able to include functions that call remote services. All right. So let's generalize mapreduce. Let's do some math. All right. When you do a traditional mapreduce, right, you map X, and X maps some result set gamma to some real numbers or some results. Right, that's what you do. And we're going to start changing this. We're going to start messing around with gamma and with the result. And the first thing we're going to do is we're going to add a context. Now, a context is something that tells you about the world you live in. Time is a great one. If I say, how many apples, again, do I have in the grocery store today? Today is my context. How many apples will I have tomorrow? Tomorrow is the context. Both are number of apples using time today, number of apples using time tomorrow. You need a context. And you may be like, well, OK, so what's the big deal? I could just use parameters. I could use these other sorts of things. Let's do an example. Let's say yesterday my portfolio was worth $43. And today my portfolio is worth $40. So what's the result? You lost money. Sad face, right? $3. Now, because obviously we're in Europe, so that's 2.72 euros. So you lost 2.72 euros. Well, suppose the FX rate yesterday was 1.2, and the FX today is 1.1. Well, then yesterday my portfolio was worth 35.83 euros, and my portfolio was worth 36.36 euros today. I made 0.53 euros. Right? So turn that frown upside down. Happy face now. So you're like, well, OK. As a mathematician, whenever you get contradictory answers, something must be wrong. So something up here is a lie. Right? What's the lie? That's the lie. You didn't lose $3. That is not a true statement. That ability, you can say you lost $3, but you can't ask any questions with it afterwards. The answer is, I have made or lost $40 in today's context minus $43 in yesterday's context. If you would like to naively flatten that to today's context and say you lost $3, that's fine. Don't ask any other questions. You've destroyed all the information of where that came from. Right? Your answer has to be context specific. You have to drag the context through. You can't add things from different contexts, because if you do, information goes away and you get this very simple example. All right, so first thing you have to do with mapreduce is add a context. Now, the next thing we're going to do is we're going to add services, right? Because we already said in that previous cartoon, by proof by cartoon, right? So in that cartoon, we said we're going to basically need to take services, and we're going to need to use those, like the weather service or something like that, as part of our mapreduce. So let's just add it in, right? So we're going to map data you have, that's the gamma, S is our services, and a context over to some results which have a context as well. Well, so what are services? Well, this is functional language conference, so might as well make them functions, right? And so what you really say is each service renders a collection of functions that map the service and all the previous services you registered before it to a result. Right? So now, why do you include the previous services? Well, you want to be able to re-leverage the previous services. So maybe service 1 is the weather thing. Maybe service 2 is the ability to figure out sea level rises. And then service 3 is the service that figures out the optimal portfolio under sea level rises. Well, now service 3 can use service 2 and service 1, right? Because we've included it in that stack. Why do you have to order them? Well, yes, you have to pick an ordering. No, we haven't solved circular references because it's not possible. All right. So this is our generalized map function. And when you think about it, it kind of makes sense, because what you're saying is, I no longer do mapreduce on data, I do mapreduce on functions. Right? You couldn't actually register, say that the gamma is effectively a set of constant functions, right? Data you have, you could just say those are const functions. And then you're just basically mapping from function space to results as opposed to data to results. And actually, that's how we think about it. You're just mapping from functional space over. So the X is data you can model, right? That's some function that maps this universe. The gamma is effectively data you have. And the F is data you can acquire. Right? There's your stuff. Now, the question is, that's really fun to write down on math, but how do you actually represent that in a program? And also, there's tons of obvious extensions here, because some of you who have done certain abstract algebra can immediately recognize this is basically an algebra. You can start doing Cartesian products, tensor products. You can start defining wacko different things, maybe even norms, and you can start to expand your algebra very, very discreetly. There's one extra piece that we're going to throw in here and introduce. Now that I've got all these services in this space, gamma, functions, and context, I may want to go somewhere, I may want to map that to another space. And I give you a really simple example here, like, customer space, gamma is the customer records, F is how much wine you bought, over time, and, C, the context is the date, and then country space is what's the country with all the wine sales in that country, right? And maybe we throw weather and things like that. These are two different spaces that maybe you cared about. Maybe countries register services that talk about their wine production in one place, but your local store has made something where they just put their own things into customer space. And you want to be able to map between them, right? That transform, you want to go between them. And what would that look like? Well, if these are my customers, Bob is in Spain, Mary's in France, Juan is in Spain, Edward's in England, and then you want to basically transform that. You can just transform that into things. Transforms change the rows, right? Instead of going customers are your rows, now it's countries are your rows. And you can hang services off each one of those. So the top is one space. The bottom is the next space. And you can have transforms that map from one to the other, right? We just made one here. It's kind of, we didn't make it, but if you see it, you know how to code it. So what do we have now? We can do this, right? And that gives us, by magic of the clicker button, that we have transforms that map things to the next set, to the next data space, And once we get to the end, we're going to apply a mapreduce function to that to get us a result. Right? Basically this. There's your abstracted data space. Right? There's your new mapreduce function. And so if you look, what is T1, T2? T1, T2, you're changing rows, you're moving stuff over here, you're going to country space, you're over in this space, and all the way TK minus 1 to TK, and then you're like, okay, mapreduce function Z. Right? It looks complex. It's actually quite simple. So this is what I call the web smack framework, and it's because you're kind of taking stuff on the web and you're smacking it together. It also stands, if you remember those gentlemen's pictures in the past, Walker, Edmundo, Burns, Spooner, McIntosh, Adams, Clark, and then K is for Calfane, who's our front-end guy whose picture didn't make the previous one. So it's just an anagram of the developers' names who started it, and now we're like 150 people working on it. But if you look, this is just a basic pipeline, and we say let IVS 0 equals root VIP. And by the way, if you recognize this as like OCaml or ML, you're, yes, correct. Well done. IVS 1, you apply a scenario. IVS 2, you apply a scenario. IVS 3, you're doing things to things, right? IVS 4. And each one takes the previous step. Well, there's a name for things like that. It's this framework up here. Those IVS 0s, IVS 1, IVS 2, IVS 3s, and IVS 4s are effectively these transformations. And that's your T1, right? I take IVS 0, and I apply it. I say the as of date is May 1st. I take IVS 2, and the as at date is May 1st as well, right? So we're setting a bitemporal time range. You're really just messing with that context. That C there, you're mapping that C. You're applying new Cs to it. So you're going from space to space. You haven't changed the gamma. You haven't changed the functions. You're just changing the context. Now you load a portfolio. Now you're changing your gamma. Now you're doing a filter. Now you're slashing it down, right? More transforms. And then, once you're done doing this, once you're done mucking around with this sort of pipe of operations, you then apply your map functions, which looks like these things. They can be almost any function on that space. And you see down here, there's IVS 4. So this is an operator being applied to IVS 4. And I'm sorry for monadic fans. We didn't put monads in the language. I wanted it, but it didn't look good. But you could actually believe that this is an operator on this, and this operator is effectively your Z operation, right? You're mapping it to 1, 2, 3, 4. You're mapping it to, right, a tuple of 4 elements. It looks even better when you put it in a pipeline, right? That's T1, that's TK minus 1, and there's your Z. So this is what was really kind of cool, was that when you do the math and you come out with this weird formula, when you're like, how would I generalize MapReduce? And then you look at how sort of computer science has developed things in functional language, you realize that effectively generalized MapReduce is the same as introducing a pipeline, right? A bunch of pipe operators as you map things to each other. And what's neat is you can implement everything in that paradigm, right? And that's kind of your core building block. So you can have pipeline 1, you can have pipeline 2, you can join those pipelines into pipeline 3, you can do all these sorts of things, but it's all kind of neatly represented in this way. And this was kind of an epiphany moment, I think, a little bit for us, because we were like, oh, wow, this is different, right? This is new. We have something kind of cool that's available here. And very clean as well. And what you immediately notice is that that's a program, right? We run it down here. And so what do you do to programs? Well, you compile them, right? You show them who the boss is, right? So it'll be the robot's day one day, but it's not now. So you compile it, and you tell it what to do. That's what we do here. You write the program, you compile it. So how do you implement a generic MapReduced paradigm? You implement it with a compiler, is the way that we found how to do it. And so traditionally you have this, and your evaluation goes that way, right? you send things down, you get the data, then you apply the next calculation, the next calculation, the next calculation to this data, and you sort of drag the data through and drag it into centralized places and start from the bottom up. But when you do a mapreduce, a generalized mapreduce, your valuation goes left to right, interestingly enough. And I'll show you why. You don't want this to think of this as an imperative ordering. So I'm going to make a function here, and I'm going to say, scenario as of May 15th, 2019, let's load this index called MSCI USA Daily. And one of the things that MSCI creates is we create what we call our ESG, environmental, social, and governance rankings for countries or for companies. And you can say things like, I don't want to own anything if they don't have women on the board, right? All sorts of metrics. So you get this answer. You may want to come and ask a question after this. Hey, what's that look with the time series? Well, you want this, right? Okay, well, now I know what it is on Jan 1, Jan 2, Jan 3. And you get your list of companies. Wow, I changed my brackets. And that gives you a list of your elements right there. If this was imperative, let's look at what would happen. You'd set a scenario, you'd load your positions, you'd filter it, and then you'd say, give me a time series. And you'd be like, I just have one date I loaded, right? You're not compatible with that. You want the ability to continue to ask questions afterwards, which means you can't make this an imperative ordering. And I have a way to make you remember it's not an imperative ordering by doing that. Initially, it was in red, but it was like really too disorienting. So, because it's non-imperative, that means, again, that you have to compile it, right? It's a program, and your execution stack isn't top-down. You have to abandon the top-down execution stack. It's non-imperative. So, the neat thing about when you do something like this is that when you find this very simple pattern that you can replicate, it lets you do a very natural fifth-generation front end, right? Because it's just a pipe operator, right? So I pipe. It's not much harder than that. So now I'm going to do the technology equivalent of free climbing. I'm going to do a live demo. We'll see how this goes. Glasses on first. So this is a neat little front end that we've designed. And I'm going to stick us into design mode. And the way that we represent the pipeline operator is we actually map here. And you see if I light this up, that little thing has a little blue box around it, and the thing on the far right does. That means that that goes to here. The way we represent a pipeline operator is we actually map from here into filters, and those filters then map to the next elements. This element right here is our pipe. And so if I apply a filtration here, suppose I say financials, then I get financials here, right? Financials disappears. I say I don't want that with financials. And so I can give myself a little ability to create a filter. If I want this to drive this, well, really what I want to do is I want to include it in the pipeline operation, right? I want to be able to force this thing, that chain of pipe operators, I want to put this at the end of this pipe operator. What I want to do is I want to be able to click on something like information technology and just show information technology over there. And so that's exactly what you do. You drag the pipe operators over. Like that. And so that's now going to send a request out, and it's going to say, hey, what's all the things? And if I click here, say like on energy, then that's going to send, and it's going to say, hey, just send the things that have energy, right? That's a completion of the pipe operator. Behind each one of these grids is a 100% complete program on its own of effectively a pipeline. an ML pipeline, which means you can do all sorts of fun things with it. Each widget is a program. Each widget is sent down individually to a server. Each program is compiled on the fly, executed, and then run against a set of services. Now, why is that important? Well, part of why the reason that that's important is because I can then pick things like energy, and I can take this and drag this to the output of screens, and then I can load entire templates of elements. And these templates that I actually load are designed by people. Here we go. Let's load this template. Are designed by people using these same sorts of pipe operations, and this allows you to start asking questions, after you've done some analysis. So you do some analysis on one screen. You want to send that analysis to the next screen. Now, a lot of times what people do is people actually send that analysis in a way that is not, how should I put it? It's not, you send the data across. We don't send the data, we send the program across. What's funny is that this screen drives these screens, but these are all independent programs. And so you can get things coming back out of order. So this screen needs that screen to compute, technically in the pipe operation, but because they're independent programs, they all execute at their own speed. And so now, in the previous screen, I applied the filter, and the filter said, oh, I want to get rid of energy from this, right? I just want to focus on the energy aspect. And that actually then was sent to this screen for further analysis. And so all of a sudden, all these really neat things that I have here, and by the way, if you look, you can see that energy is this monstrously overexposed thing now because I nuked it, right? I got rid of it. All of these sorts of elements that I have, all these sorts of calculations that are available, are now available that someone can put in, can be asked as a compositional element on top of my previous questions. So let me go back to this. So this lets you do some really, really, really cool things because you have a program now. And so with this program, you can go embed that program in different places. So here, you can go up to this thing, you can copy the JSON query, you can export it, and then you can go into PowerPoint and paste it. When you paste that query, that goes out and makes a query to the server. Now, here he just shut the Microsoft PowerPoint down and is going to reload it. And now it's loading, but it's going to re-execute that query again. It's going to submit that query down. And now you're going to render the PowerPoint again. So you come in the next day to your PowerPoint, you open it up, and all the data automatically refreshes because that program is independently executable. Yeah? That's quite neat. This gives you a lot of power to go embed pieces of program into different places. And that's an HTML object that's inside of there as well, so you can go embed that lots of different places. You've destroyed the workflow with the front end, and so therefore any component is hostable outside of the front end as well, which is extremely powerful. And in fact, you can just use it as an API query as well. So, time check. Oh, yeah. So how does the machine work then? Machine starts with some pre-built-in functions. And then, like we said, you have a bunch of services. You can add a service API layer. And you can start registering all of your different systems, all of your different services. These can be in different data centers, wherever they are. You can just actually begin registering. We believe there's only 4 APIs, which isn't that difficult to believe. There's that T API, right? There's the X API. You want to introduce a new X, a new mapreduce function. There's the gamma thing, right, which allows you to introduce new gamma elements. And then there's a way to actually join data with the gamma, right? So technically, we could have made it 3, but. So here you go. Process X, process Y, and you get a functional library on the right-hand side of all of your registered services. Then you ask a question, right? That question, again, is just the program. You send the program down, and that program goes and it gets compiled on the fly, builds a graph, and that graph gets shipped over to the execution engine. And when I say compiled, we really compile it down to bytecode. Right? And actually, we cache the program. We pull the parameters out. We cache the program. And then if you ever need to access that program again, you just go with like different parameters. So suppose instead of like 8, you use 9 or something like that. And then you add a context. And then you process. And that processing occurs, brings the value back, and then you're done. Now, the neat thing is that once you've done this, this gives you some pretty neat capabilities. And we'll go back to a demo here. And so suppose that I go in. So I've got these things on the right. I'm going to add a field. And you can start adding fields like var. Let me get a risk here. There we go. And the important thing to know about this is not what var is, but the fact that it's parameterizable. You see here we have things like decay factors, which are doubles. You have holding periods, look back, confidence intervals, display periods, and the like, all sorts of things. And so you can add and you can put in your own set of functions onto that. And why that's taking a little bit of time, by the way, is that's actually going dynamically back to the var service and calling that and actually calculating it. Now, once you do this calculation, those are functions, right? We didn't register data, we registered functions. Those are the parameters which I showed you that's on that function var. So if I want to change it, I just go here, I grab that. Oop, there we go. OK, I got myself a little thing. So now if I type in 0.9667 or something like that, that actually re-executes that functional call. So you can expose the parameters directly. So you can make a pipeline, expose your parameters. So you're really writing a true functional front end. And now you notice that took a few seconds. If I actually replace this and I do the following, I take it back to 0.95 where it was before, and I just click out. Well, now it's instantaneous, right? Because you don't need to go back to the services. You have it in your local repository. So this ability then to generalize mapreduce turns out to be effectively a pipeline operator, a functional language, right? Where you actually do functions, you actually compose functions on functional language, compile it, and execute it, and then get your results that way. So it's a complete different new paradigm, we think. And again, if it's not, you can humiliate me now or later. So, all right, thank you.
OK, thanks very much. Let me just check if we have some questions here, and otherwise we can take them from the audience. Let me just reload. OK. So one quick question from me then, but you started off with working in big data gets you grumpy. Is that still the case, or are you now more happy? I see you all the time smiling, so
yeah, not as grumpy as this guy is. So that's my.
OK. We have one question here. OK, so one question is the tool that you were showing, is this commercially available, or is it free for use?
It's commercially available. We're actually, and the reason it's still, you know, my end goal with this tool, it actually launched 1 week ago. I would like to open source it at some point in the not so long future, 12 to 18 months. We are still working on the syntax of the language, and so we still want to formalize that down, embed it down with some good syntactical capability. And then once your syntax is effectively done and the paradigm is done, the idea would be to open source it, but it's available commercially at this point. Yep, you can call us up and we'll sell it to you.
OK, thank you very much. Any questions from the audience? So if you have a question, raise your hand so I can bring the microphone to you. Yeah, I see somewhere there. So, in the middle of the room.
really bright up here. You can't really see.
Hi, thank you for the presentation. So I was curious, how does the back-end processing and language framework differ from something like Apache Spark? Seems very similar in DAG and pipeline construction.
It is. It's except that it constructs off of remote functional calls at its core, right? So there's two pieces. One is that the pipeline is not imperative, right? So that the pipeline actually is reorderable by commutativity rules, right? So that's a big difference, and that's a big change. So that ability to sort of ask future questions later, and the pipeline sort of recompiles itself. And then the second way is that we actually, the abstract treatment and the transformation of your data spaces, this concept of, you have gamma, F, and C, and you can map that to a new gamma, F, and C. And so it's almost like the abstraction of being able to map, say like, Spark is on top of Hadoop. Imagine that the result of a calculation was you go to a completely different Hadoop instance that works on completely different data. Suppose you have your Spark representation over here of customer data, and over here you have country data, and you sort of map that invariantly in top of that. And then actually the standardization of the nomenclature and the APIs allows, and this is part of our future business model, is to allow anyone at any point to hook services in arbitrarily, and those services seamlessly work because you're enforcing it with the mathematical construct. So by actually being more specific, by forcing very distinct API patterns and very distinct transformation patterns, like in the math there, you actually get a lot of natural extensibility, and you can register certain frameworks and say, you can now contribute to this, and we don't even have to go through a validation step to ensure that it works, because the math will force you. If you can implement it in the paradigm, it will by nature work and be composable with everything else. So does that answer your question? One's a kind of a generalization of the other, so they're going to be very naturally related. If they weren't related, well, it wouldn't be a generalization, right? And so I think they're building to it from the almost more the imperative side, and we're coming at it from the functional side. But yeah, they're not that far apart.
Thank you. And then the follow-up question is, what type of benchmarking and data throughput have you experienced with the system?
Yeah, so it is nowhere close to what you get with these traditional mapreduce paradigms that you have right now, right? Because we're starting with a compilation step and then an execution step. And they've got like a 15-year head start on us in optimization routines, right? And so one of the big areas of active research, and why we're hiring so many people in London and the like, is that we have some interesting theoretical ideas about how you distribute programs, right? Because you're not really distributing, you're kind of distributing calculations, but you're distributing chunks of programs. And because you compile, and now you want to run that on 10 different servers. Well, it's a program. So you need to be able to break that program into pieces and have different pieces execute on different servers. And so we're hoping with that we can start to get that element. What this allows you to do is it allows you to ask extremely complex brand new questions and get results back in a reasonable period of time. If you have more specific problems that you've already sort of pre-configured your data to shard on and stuff like that, not the platform for you, right? Not what you're going to want. You're going to want to be able to control your data environment. You're going to want to be able to control where you actually distribute these things and distribute those calcs there and get massive speed. If you kind of don't know what question you're going to wake up the next morning and ask, which happens a lot in certain industries, then this is kind of a better paradigm because you don't have to pre-optimize your data environment. And also, again, it uses data that you don't have as well. It calls to the service layers.
Thank you.
Any more questions? Yeah, in the front of the room, please. In the front of the room. I think I saw some movement here. There we go. All right.
Hi, thank you for your speech. It was really interesting. I was curious. If you use this tool, are you bound to use the MSCI data, or can you just feed the tool with your own data?
You just use the tool with your own data. We've actually had customers that have come to us and we're like, this is great, but we don't want any of your data. And we're like, all right. To me, it's just a generic thing. I mean, it's use it for, I don't know, tracking toilet paper sales at Tesco or something like that. I mean, who cares? It's kind of abstracted, and we're pretty open to exploring new uses for data for it, because that our market is more like financial companies, and so if people are interested in using it for things outside of that, yeah, totally open for using it with other data.
Okay, I think I saw 2 hands here, or was it just 1? No more questions? Okay, then we're done. Then we can go for a coffee break. So give a warm applause to Trent.
Thank you.
And we will continue.